Hey everyone, I'm Alex Huth. I'm glad to be back here. It's really fun to see everyone here again and hear about everything that's happening here. It's super fun. So I just started a couple of months ago as a new assistant professor at UT Austin. So I'm going to tell you a little bit about the work I've been doing the last year, mostly before I started my new lab, and then a little bit about my plans for the future. So I wanted to start first with a recap of sort of what my work is about generally and what I've been looking at. So I study human cortex using fMRI, which is like 1 million miles away from what most people here are doing and talking about, but that makes it fun, right? So I'm interested in the language system. I'm interested in how the brain represents the meaning of language, the meaning of words that we hear. The way that I go about studying this is I show people natural stimuli or make people listen to natural stimuli like stories, and I record their brain activity continuously using fMRI while they listen to a couple hours of stories, and then use a variety of machine learning techniques to extract features from the stories that we think might be represented in the brain, and then to build models that predict the activity of the brain as a function of these features, and then examine these models to map out which kinds of features, which kinds of words are represented in different parts of Cortex. This is showing a map from a few different subjects. The different colors here correspond to selectivity for different kinds of words. So you can see that we actually have a lot of similarity across these subjects in terms of sort of patterns of selectivity across the brain. So this is the story with just language, and this has been really interesting, and there's a lot of fun things to play with here in terms of how do we extract features, how do we fit these models, and how do we sort of learn about the cortical maps from a group of subjects. I think these are all interesting sort of machine learning topics. But the thing I wanted to talk about that I've been working on recently is investigating the relationship between language and vision, which I think is a really super interesting and basic topic. It's like you hear the word for a thing, you see a thing, how are these two things related? So I actually got kind of lucky in that I had a lot of subjects where I'd scanned them doing this language study, and I'd also happened to scan some of these same subjects while they were watching a few hours of natural movies for another study. This is the good thing about scanning people in your own lab, is it happens to overlap. And it turns out that I can fit the same kinds of models to both of these data sets. So I can label all the things that happen in the movies and then treat those as if they're words that the person is hearing, right? So fit the same kind of language model and then compare the responses across these two modalities. And when we did this, initially we just looked at like where are they correlated, and we found a kind of boring result in that there's some places around the edge of visual cortex where you get responses to both words and pictures for the same things, and we thought this is fine, this is just another replication of the same result that people have seen many times before. But then I did a little bit of a more targeted analysis, and I found something that I think is really cool and really interesting. So if we look at a specific category, so in this case I looked at places, so representations of sort of visual places. So this is buildings and scenes and words that describe those places. So there's a collection of brain areas that canonically respond to these things, including retrosplenial cortex, which we just heard about. It's right here, the occipital place area and the parahippocampal place area. And what we see when we look at place responses in language and in vision is actually that they're only partially overlapping. So within each of these areas, the colors here, they're red for voxels, parts of the brain that only respond to visual places, blue for just language, white for both, and black for neither. And across each of these place areas, we actually see this gradient where the back part of the area is mostly like only visually selective. There's mixed selectivity in the middle. And then outside of these areas, we see strong selectivity for place words, so like the language that describes places. And this is really cool. This is really exciting, I think, because it says something about what the boundary of visual cortex is really doing. Like what happens when visual cortex stops? Does something else just take over, or is it something that's totally unrelated to vision? No, it turns out that it's actually you get representations of almost the exact same things that were represented just next to that visually, but in other modalities or in a sort of amodal way. And so we've now explored this much further. I've been working with a grad student in my old lab and Jack Allen's lab at UC Berkeley named Sarah Popham, who's been investigating this. And we really found that this seems to be a general property of the boundary of visual cortex, that in fact, encircling the entirety of visual cortex, we have these little gradients from purely visual representation to purely non-visual representation of the same categories. And they're aligned all around the edge of visual cortex. So that's the new thing that I've been doing that's cool. And then I wanted to take just a moment to talk about what sort of future directions I'm going in my lab and what kinds of fun things I'm working on. And this major project that I'm just setting up and gearing up to start collecting data on, this is really, I'm drawing a lot of inspiration from what you guys are doing here at the Allen Institute, and I think that's fantastic and a great inspiration to me. So, a real limitation on the kind of work I do is that the model complexity is totally limited by the amount of data that we have, right? So the kinds of models that we can fit is really determined by just the number of stimuli that we can play for our subjects. So with the kind of small amount of data, that's 2 to 4 hours of data per subject, we're trapped in this sort of linear model framework, and we have to do a lot of feature engineering. We have to guess what kinds of features are represented in the brain. It just comes down to be this sort of guess and check problem of trying out different feature spaces and seeing what works. And I don't want to do that anymore. That's hard, and this is just involves a lot of serial guessing things. So what if we can just change this picture entirely? So my goal is to try to see, can we collect 200 hours of data per subject instead of 2 hours of data? This is going to take a lot of scanning for a few individual subjects. I'm probably going to be one of the first subjects, and that's fine. But once we do this, we can move into this totally different regime where we are fitting nonlinear models that instead of extracting features that we think are represented in the brain, we let the models figure out what the features are. And we move into the realm of architecture engineering, which is really where a lot of ML is moving these days, where we can design neural network type models and then tweak the architecture until we find things that actually capture what the brain is doing instead of trying to find specific features. And this has totally changed how sort of the computer vision world is working, and I think this is going to change how we study language as well. And so getting this all to work, this seems crazy, but it's actually not that hard. You just put a person back in an MRI scanner a bunch of times. It's insane to me that nobody has done this yet, but nobody has. But I think there's some interesting challenges that we have to address, and so I'm really trying to build out these kind of pipelines for annotating stimuli. So we need many, many hours of stimuli, obviously, collecting the data, and then estimating models for these things sort of continuously. So this is a lot of fun. Thank you all for listening, and I'm sure I'll see you all around.